In algebra, a quartic function is a function of the form where a is non-zero, which is defined by a polynomial of degree 4, called quartic polynomial. Sometimes the term biquadratic is used instead of quartic, but, usually, biquadratic function refers to a quadratic function of a square, having the form. A quartic equation, or equation of the fourth degree, is an equation that equates a quartic polynomial to zero, of the form where a permel 0. The derivative of a quartic function is a cubic function. Since a quartic function is defined by a polynomial of even degree, it has the same infinite limit when the argument goes to positive or negative infinity. If a is positive, then the function increases to positive infinity at both ends, and thus the function has a global minimum. Likewise, if a is negative, it decreases to negative infinity and has a global maximum. In both cases it may or may not have another local maximum and another local minimum. The degree 4 is the highest degree such that every polynomial equation can be solved by radicals. History: Lodovico Ferrari is credited with the discovery of the solution to the quartic in 1540, but since this solution, like all algebraic solutions of the quartic, requires the solution of a cubic to be found, it could not be published immediately. The solution of the quartic was published together with that of the cubic by Ferrari's mentor Gerolamo Cardano in the book Ars Magna. The Soviet historian I. Y. Debman claimed that even earlier, in 1486, Spanish mathematician Worms was burned at the stake for claiming to have solved the quartic equation. Inquisitor General Tomás de Torquemada allegedly told Worms that it was the will of God that such a solution be inaccessible to human understanding. However, Beckmann, who popularized this story of Debman in the West, said that it was unreliable and hinted that it may have been invented as Soviet anti-religious propaganda. Beckmann's version of this story has been widely copied in several books and internet sites, usually without his reservations and sometimes with fanciful embellishments. Several attempts to find corroborating evidence for this story, or even for the existence of Worms, have failed. The proof that 4 is the highest degree of a general polynomial for which such solutions can be found was first given in the Abler-Euro-Ruffny theorem in 1824, proving that all attempts at solving the higher-order polynomials would be futile. The notes left by a Permelvarist Galois prior to dying in a duel in 1832 later led to an elegant complete theory of the roots of polynomials, of which this theorem was one result. Examples: the Cassini oval, which is the locus of points all of which have the same product of distances to a pair of foci, is a quartic in two variables. The Cartesian oval, which is the locus of points all of which have the same weighted sum of distances to two foci, is a quartic in two variables. Lemma-sectionons and lemma-scates are quartics in two variables. Llama copyright S special quartic, and more generally the squircle, appears as a square with rounded corners when plotted. Other examples of bivariate quartics are given in the article quartic plane curve. Applications: each coordinate of the intersection points of two conic sections is a solution of a quartic equation. The same is true for the intersection of a line and a torus. It follows that quartic equations often arise in computational geometry and all related fields such as computer graphics, computer-aided design, computer-aided manufacturing and optics. Here are examples of other geometric problems whose solution amounts of solving a quartic equation. In computer-aided manufacturing, the torus is a shape that is commonly associated with the end mill cutter. To calculate its location relative to a triangulated surface, the position of a horizontal torus on the z-axis must be found where it is tangent to a fixed line, and this requires the solution of a general quartic equation to be calculated. A quartic equation arises also in the process of solving the crossed ladders problem, in which the lengths of two crossed ladders, each based against one wall and leaning against another, are given along with the height at which they cross, and the distance between the walls is to be found. In optics, Alhazen's problem is given a light source and a spherical mirror. Find the point on the mirror where the light will be reflected to the eye of an observer. This leads to a quartic equation. Finding the distance of closest approach of two ellipses involves solving a quartic equation. The eigenvalues of a 4a, Four matrix are the roots of a quartic polynomial, which is the characteristic polynomial of the matrix. The characteristic equation of a fourth-order linear difference equation or differential equation is a quartic equation. An example arises in the Timoshenko-Rayleigh theory of beam bending. Intersections between spheres, cylinders, or other quadrics can be found using quartic equations. Inflection points and golden ratio, letting f and g be the distinct inflection points of a quartic, and letting h be the intersection of the inflection secant line fg in the quartic, nearer to g than to f, then g divides fh into the golden section. Moreover, the area of the region between the secant line and the quartic below the secant line equals the area of the region between the secant line and the quartic above the secant line. One of those regions is disjointed into subregions of equal area. Solving a quartic equation. Equals nature of the roots equals, given the general quartic equation. With real coefficients, and the nature of its roots is mainly determined by the sign of its discriminant. This may be refined by considering the signs of four other polynomials, such that is the second-degree coefficient of the associated depressed quartic, such that is the first-degree coefficient of the associated depressed quartic, which is 0 if the quartic has a triple root, and which is 0 if the quartic has two double roots. The possible cases for the nature of the roots are as follows. If then the equation has two real roots and two complex conjugate roots. If then the equation's four roots are either all real or all complex. If p0 or d greater than 0, then there are two pairs of complex conjugate roots. If then either the polynomial has a multiple root, or it is the square of a quadratic polynomial. Here are the different cases that can occur. If p0 or, there is a real double root and two complex conjugate roots. If and dA permel 0, there is a triple root and a simple root, all real. If d equals 0, then, if p0 and q equals 0, there are two complex conjugate double roots. If all four roots are equal to. There are some cases that do not seem to be covered, but they cannot occur. For example 0, p equals 0 and dA permel 0 currency is not one of the cases. However, if 0 and p equals 0, then d greater than 0, so this combination is not possible. Equals general formula for roots equals. The four roots for the general quartic equation with AA permel 0 are given in the following formula, which is deduced from the one in the section solving by factoring into quadratics by back-changing the variables and using the formulas for the quadratic and cubic equations, where p and q are the coefficients of the second and of the first degree respectively in the associated depressed quartic, and where, with, and where is the aforementioned discriminant. The mathematical expressions of these last four terms are very similar to those of their cubic counterparts. Special cases of the formula, if the value of is a non-real complex number. In this case either all roots are non-real or they are all real. In the latter case, the value of is also real, and one may prefer to express it in a purely real way, by using trigonometric functions, as follows. Where if and the sign of has to be chosen to have, that is, one should define as maintaining the sign of, if then one must change the choice of the cube root in order to have. This is always possible except if the quartic may be factored into the result is then correct, but misleading because it hides the fact that no cube root is needed in this case. In fact, this case may occur only if the numerator of is 0, in which case the associated depressed quartic is biquadratic. It may thus be solved by the method described below. If and thus also at least three roots are equal, and the roots are rational functions of the coefficients. If and the above expression for the roots is correct but misleading, hiding the fact that the polynomial is reducible and no cube root is needed to represent the roots. Equals simpler cases equals. Reducible quartics, consider the general quartic. It is reducible if q equals rs, where r and s are non-constant polynomials with rational coefficients. There are two ways to write such a factorization, either or. In either case, the roots of q are the roots of the factors, which may be computed by solving quadratic or cubic equations. Detecting such factorizations can be done by using the factor function of every computer algebra system. But, in many cases, it may be done by handwritten computation. In the preceding section, we have already seen that the polynomial is always reducible if its discriminant is 0. A very special case of the first case of factorization is when a0 equals 0. This implies that x1 equals 0 is a first root, b3 equals a4, b2 equals a3, b1 equals a2, b0 equals a1, and the other roots may be computed by solving a cubic equation. If then and we have a factorization of the first kind with x1 equals 1. Similarly, if then and we have a factorization of the first kind with x1 equals -1. Once a root x1 is known, the second factor of the factorization of the first kind is the quotient of the Euclidean division of q by x(x1). It is. If our small integers, a factorization of the first kind is easy to detect, if with p and q prime integers, then q divides evenly a4, and p divides evenly a0. Thus, computing for every possible values of p and q allows to find the rational roots, if any. In the case of two quadratic factors or of large integer coefficients, the factorization is harder to compute, and, in general, it is better to use the factor function of a computer algebra system. Biquadratic equations, if then the biquadratic function defines a biquadratic equation, which is easy to solve. Let then q becomes a quadratic qn. Let n be the roots of q. Then the roots of our quartic q are. Quasi-palindromic equation, the polynomial is almost palindromic, as it is palindromic if m equals 1. The change of variables in produces the quadratic equation as the quartic equation. May be solved by applying the quadratic formula twice. Solution methods equals. Converting to a depressed quartic, for solving purposes, it is generally better to convert the quartic into a depressed quartic by the following simple change of variable. All formulas are simpler and some methods work only in this case. The roots of the original quartic are easily recovered from that of the depressed quartic by the reverse change of variable. Let be the general quartic equation we want to solve. Dividing by a4 provides the equivalent equation. With substituting x by gives, after a simple term regrouping, the equation where if y1, y2, y3, y4 are the roots of this depressed quartic, then the roots of the original quartic are. Ferrari's solution, as explained in the preceding section, we may start with a depressed quartic equation. This depressed quartic can be solved by means of a method discovered by Lodovico Ferrari. The depressed equation may be rewritten. Then, we introduce a variable y into the factor on the left-hand side by adding to both sides. After regrouping the coefficients of the power of u in the right-hand side, this gives the equation, which is equivalent to the original equation, whichever value is given to y. As the value of y may be arbitrarily chosen, we will choose it in order to get a perfect square in the right-hand side. This implies that the discriminant in u of this quadratic equation is 0, that is y is a root of the equation, which may be rewritten. This is the resolvent cubic of the quartic equation. The value of y may thus be obtained from the formulas provided in the article cubic equation. When y is a root of equation, the right-hand side of equation the square of. However, this induces a division by 0 if this implies and thus that the depressed equation is biquadratic, and may be solved by an easier method. This was not a problem at the time of Ferrari, when one solved only explicitly given equations with numeric coefficients. For a general formula that is always true, one thus need to choose a root of the cubic equation such that this is always possible unless for the depressed equation x4 equals 0. Now, if y is a root of the cubic equation such that equation may be rewritten, and the equation is easily solved by applying to each factor the formula for quadratic equations. Solving them we may write the four roots as where and denote either plus or. As the two occurrences of must denote the same sign, this leave four possibilities, one for each root. Therefore the solutions of the original quartic equation are Solving by factoring into quadratics, one can solve a quartic by factoring it into a product of two quadratics, which do not need to have rational coefficients. Let. By equating coefficients, this results in the following set of simultaneous equations. This can be simplified by starting again with a depressed quartic where, which can be obtained by substituting for, then, and. One can now eliminate both and by doing the following. If we set, then this equation turns into the resolvent cubic equation, which is solved elsewhere. Then, if P is a square root of a non-zero root of this resolvent, the symmetries in this solution are as follows. There are three roots of the cubic, corresponding to the three ways that a quartic can be factored into two quadratics, and choosing positive or negative values of for the square root of merely exchanges the two quadratics with one another. The above solution shows that the quartic polynomial with a zero coefficient on the cubic term is factorable into quadratics with rational coefficients if and only if either the resolvent cubic has a non-zero root which is the square of a rational, or is the square of rational and c equals 0. This can readily be checked using the rational root test. Solving by Lagrange resolvent, the symmetric group S4 on 4 elements has the Klein 4 group as a normal subgroup. This suggests using a resolvent cubic whose roots may be variously described as a discrete Fourier transform or a Hadamard matrix transform of the roots. See Lagrange resolvents for the general method. Denote by xi, for I from 0 to 3, the four roots of. If we set, then since the transformation is an involution we may express the roots in terms of the 4c in exactly the same way. Since we know the value SO equals A over 2, we only need the values for S1, S2 and S3. These are the roots of the polynomial. Substituting the c by their values in term of the xi, this polynomial may be expanded in a polynomial and s whose coefficients are symmetric polynomials in the xi. By the fundamental theorem of symmetric polynomials, these coefficients may be expressed as polynomials in the coefficients of the monic quartic. If, for simplification, we suppose that the quartic is depressed, that is A equals 0, this results in the polynomial. This polynomial is of degree 6, but only of degree 3 in S2, and so the corresponding equation is solvable by the method described in the article cubic function. By substituting the roots in the expression of the xi in terms of the c, we obtain expression for the roots. In fact we obtain, apparently, several expressions, depending on the numbering of the roots of the cubic polynomial and of the signs given to their square roots. All these different expressions may be deduced from one of them by simply changing the numbering of the xi. These expressions are unnecessarily complicated, involving the cubic roots of unity, which can be avoided as follows. If S is any non-zero root of, and if we set, then we therefore can solve the quartic by solving for S and then solving for the roots of the two factors using the quadratic formula. Note that this gives exactly the same formula for the roots as the preceding section. Solving with algebraic geometry, an alternative solution using algebraic geometry is given in, and proceeds as follows. In brief, one interprets the roots as the intersection of two quadratic curves, then finds the three reducible quadratic curves that pass through these points, and then use these linear equations to solve the quadratic. The four roots of the depressed quartic may also be expressed as the x-coordinates of the intersections of the two quadratic equations, that is, using the substitution that two quadratics intersect in 4 points is an instance of Bar-Copyright-Zout's theorem. Explicitly, the 4 points are for the four roots of the quartic. These 4 points are not collinear because they lie on the irreducible quadratic and thus there is a one-parameter family of quadratics passing through these points. Writing the projectivization of the two quadratics as quadratic forms in three variables. The pencil is given by the forms for any point in the projective line in other words, where and are not both 0, and multiplying a quadratic form by a constant does not change its quadratic curve of zeros. This pencil contains three reducible quadratics, each corresponding to a pair of lines, each passing through two of the 4 points, which can be done different ways. Denote these given any two of these, their intersection is exactly the 4 points. The reducible quadratics, in turn, may be determined by expressing the quadratic form as a 3 matrix. Reducible quadratics correspond to this matrix being singular, which is equivalent to its determinant being 0, and the determinant is a homogeneous degree 3 polynomial in and corresponds to the resolvent cubic. See also, linear function, quadratic function, cubic function, quintic function, polynomial, Newton's method. References. Further reading, Cardano, Gerolamo, Ars Magna or the Rules of Algebra, Dover, ISBN 0-486-67811-3, Fawcett, William Mark, A Geometric Interpretation of the Solution of the General Quartic Polynomial, The American Mathematical Monthly 103, 51 doi, 10.2307/2975214, Cite Searx, 10.1.1.111.5574, Nichols, R.W.D. The Quartic Equation, Invariance and Euler's Solution Revealed. Mathematical Gazette 93, 66 €75. Carpenter, W. On the Solution of the Real Quartic. Mathematics Magazine 39, 28 €30 doi, 10.23007/2688990. Shmeikov, S.L. A Universal Method of Solving Quartic Equations. International Journal of Pure and Applied Mathematics 71, 251 €259. External links, Quartic formula as 4 single equations at planetmath.org. Ferrari's achievement,